This video will focus on the conservation of momentum. I'll be going over three main things: what momentum actually is, calculating momentum, and the principle of conservation of momentum. Right then, you need to know that momentum is a property of moving objects. It's a measure of the motion of those objects. Momentum is equal to the mass multiplied by the velocity. In symbol form, that's P equals mv. Now we know that the units for mass is kilograms, the units of velocity is meters per second. We can use that to find out the units for momentum, which is kilograms meters per second. Remember, that's not kilograms per meters per second, that's kilogram meters per second. So here I have a scenario with two different trolleys going in two different directions. I want you to tell me the momentum of this system. Pause the video now and have a little go yourself. So the first thing I would have done is designate a direction as being positive. So I'll say that moving to the right is positive and moving to the left is negative. So the pink trolley is moving in the positive direction and the blue trolley is moving in the negative direction. Then we just split this into two different questions, so let's just focus on the pink trolley on the right for now. Its momentum will be equal to the mass, 3 kilograms, multiplied by the velocity, 6 meters per second. That gives us 18 kilograms meters per second. Now do the same on the left with the blue trolley. We have a velocity of 9 meters per second, but remember it's moving in the negative direction. That's a negative 9 meters per second. And we have a mass of 2 kilograms. That gives us a momentum of 2 multiplied by minus 9, which gives us negative 18 kilograms meters per second. Overall, to get the momentum, we just sum these values. So we get that the overall momentum is minus 18 add 18, which is 0. So there's no overall momentum. This was a bit tricky, but the lesson here is that you need to remember your signs. Remember what is a vector and what is a scalar. Velocity, and thereby momentum, are both vectors and so have a direction. Moving on to conservation of momentum, here's a fantastic example of momentum being conserved. This is a Newton's Cradle. You've probably already seen one of these before. Some of you may actually have one of these at home, but it's a fantastic example of how momentum is being conserved. You're lifting one ball up from one side and letting go. It crashes into the other balls, stops moving, and then a ball on the other end lifts off. Now, the reason you can see here that momentum is being conserved is that we've lifted a ball up of a certain mass. All of these balls are of the same mass. Once it crashes into the balls in the middle, the ball that lifts on the other end also has the same mass. That mass is being conserved. But the ball also lifts up at the same velocity, just as the velocity of the ball crashing into the balls in the middle. That momentum is actually being transferred through the balls into the middle, out the other end. No momentum is being lost. There's no momentum being gained. It's only being transferred in this system. Now, in real life, these balls would not go on forever. You've probably seen how they decay over time. They lift off smaller and smaller until eventually they're not moving at all. And that's because they're losing energy to surroundings. You can hear them. You can hear the sound of them. There may be some friction as well when the balls are bumping into each other. They may be heating up. They may be losing energy through there. So they're losing some kinetic energy. And that's why over time they'll decay in real life. In a perfect example, this is how they would behave. So like I just said, momentum is always conserved in any event, such as in collisions and explosions. The total momentum before the event is equal to the total momentum after the event in a closed system. That just means you're not putting energy into it and you're not taking energy out of it, like that example with the Newton's Cradle. There are a couple more examples of everyday life where momentum is conserved below, and I'm sure you can think of many other ones, but momentum is conserved everywhere in the universe. Like when you jump up on Earth, you're pushing the Earth away, the Earth is pushing you away. You move at a certain velocity, you have a certain mass. The Earth also moves at a certain velocity, and it also has a certain mass. But its mass is absolutely incomprehensible compared to your mass. So it moves at the most negligible velocity you could think of, and you have virtually no impact on it. So another example where momentum is conserved is recoil. Here I've got a cannon. It's going to fire a cannonball. The cannonball shoots out forwards and the cannon moves back. This is an example of recoil. It's a type of explosion event. So what's happening here is that when the gunpowder in the cannon explodes, the ball shoots forwards. Now there's a sudden gain in momentum. Initially there is no momentum in the system. That momentum needs to be counteracted by the cannon moving backwards. Now the ball has a very low mass compared to the cannon, so it moves at a much greater velocity. The cannon moves backwards in the opposite direction at a much lower velocity because its mass is so big. The momentum forwards of the ball is counteracted by the momentum backwards of the cannon. They're both equal. That's because they need to cancel each other out so that they can equal the momentum before this explosion, which was 0. For now, I just want you to understand that this is an example of conservation of momentum. Later in another video, I'll go over in a more mathematical method of proving this conservation of momentum. To summarize, I've gone over momentum and what it actually is. It's the mass multiplied by velocity. Its units are kilograms meters per second. I've gone over what the principle of conservation of momentum is, which is saying that the total momentum before an event is equal to the total momentum after that event. And I've emphasized the importance of having your positive and negative directions, keeping in mind your directions when you're using vectors, such as velocity and momentum.